attend the online class by having proper the material with you. Have a long notebook with you, so that important things that we cover in online class can be notes can be taken. Though material I am presenting is available to you, but I suggest everybody to uh, write down the important points that we cover here. Okay. Okay, all right. Today's topic is biasing using a collector to base feedback resistor. Just look into the previous topics that we have covered. The classical discrete circuit bias, which is also called as voltage divider bias. This topic we covered in the last class. So just prepare uh, both the theoretical things and problems from examination point of view. So this is the topic of today's class, and this again module 1 is very lengthy module, which contains so many chapters. Okay, specifically this module 1 contains 4 chapters. So we are just discussing one of that, which is BJT biasing. Under BJT biasing we already covered discrete bias circuit arrangement. The second type of biasing circuit is biasing using collector to base feedback resistor. The name itself suggests that there is a resistor, which we are calling here as a feedback resistor, that's connected between the collector and base. Okay, so that's the type of circuit we are discussing in today's class. Let me move straight away into the material. Okay, before we move on to the actual topic, which is biasing using a collector to base feedback resistor, we just want to discuss other bias circuits. And this material, you can see that which I am presenting. I'll just zoom it a little bit. Hope everybody can see this material. If you are unable to see, you can just ask me so that I can enlarge it. So it's good for visualization purpose. Okay, straight away this content is taken from the textbook called Cedra Smith. Okay, so Cedra Smith is the prescribed textbook for this subject. 90% syllabus is covered from the textbook. Okay, so just students can download e-copy. Okay, if you are feeling difficulty to access from the library. All right, 3.5.2, which is a 2 power supply version of the classical bias arrangement. Earlier we have seen just a bias arrangement based on 1 power supply, but right now we are discussing a bias arrangement which is based on 2 power supply. In fact, this is a drawback again. So more the power supply you use, the circuit is not economic. So always single power supply circuit is good. But since this provides the background for the collector to base bias circuit, we are just discussing this a 2 power supply version of classical bias arrangement. The circuit is nowhere different from the previous circuit, classical bias circuit arrangement, except there is a 2 power supply. Namely, you can see here in the circuit, which is minus VEE. One of the power supply is plus VCC, the other one is minus VEE, and this is the biasing circuit arrangement that uses 2 power supply. And you can see here the BJT is connected in common emitter mode. As you can see here, the emitter is okay, which goes to the power supply in this case. Otherwise normally this will be grounded. Okay, and now you can see there is a resistor which is RB. Okay, this is not like in classical bias arrangement. We have seen that RB is nothing but R1 parallel with R2. Okay, so but here this RB is different from that. In previous circuit we called RB or R Thevenin as R1 parallel with R2, but here this resistor is different from that. And now here this is needed only if the signal has to be capacitively coupled to the base. So when we apply here the AC signal, okay, through capacitive coupling, if I use the capacitive coupling to apply the AC signal like this, the AC signal which needs amplification here, then this RB is required. Okay, otherwise this RB is not required. This RB will straight away goes to the ground. We should know when RB is required, and we are supposed to use accordingly. Okay, all right. So this is, I will just remove this a signal part. This is capacitive coupling of input signal. Alright, so this is a biasing scheme that uses two power supply. As I told you already, the VCC is connected to the collector of the transistor, and that's RC through the resistor RC. And this expression IB, we have discussed this in earlier class also. IB is equal to IE divided by 1 plus beta. This in fact we have derived in the previous classes, and we have shown that how IB is equal to IE divided by 1 plus beta. Students are advised to go through this IB expression from the previous class material. Okay, and other things is, from the base side we have only one resistor, and between base and emitter there is a voltage which is VBE, typically 0.7 volts VBE. You have to design bias circuit such that even though the variation of VBE, the current here should be maintained constant here. Okay, either emitter current or collector current. We can sense in this BJT the collector current and emitter current both are equal, approximately they are equal. Okay. In fact, the emitter current will be larger little bit, maybe the 5% will be larger than the collector current. But in most of our analysis we will assume that these two currents are going to be equal. Let me give an example. In a practical example, if this is going to be, say, this is 1 milliampere, and this will be practically, if you look at circuit, this will be 0.99 milliampere. Now you can see the difference here between these two currents here. So difference is very small, that's why we, in most of our analysis, will assume that IC and IE both are equal. Okay, now we will go to the circuit. We have seen the description of this biasing arrangement, which is based on two power supply. Okay, one is positive power supply, other one is negative power supply. Negative power supply that goes to the emitter we have labeled as minus VE. Okay, that means here the supply should be connected somewhat like this, negative first and a positive like this, negative, positive. The battery should be connected in this manner. Probably if you have developed any op-amp circuits, you would have come across this minus VE supply, how it looks. And here you can see that since positive VCC is there, here this plus VCC will be something like this. Okay, so positive goes to the collector here, the resistor RC here. Negative will get grounded here. Okay, so this is the equivalent of this plus VCC. So this is plus VCC, and this is minus VE is equivalent to this. So this is minus VE. Okay, that's how the circuit should be interpreted. Alright, so this is simple bias arrangement compared to other bias arrangement that we have discussed in earlier class, classical bias arrangement. This is going to be very simple because we don't have any voltage divider network here. We have only the resistor which is RB. Okay, but only thing is this uses two power supply. Now let us go to the circuit analysis here. How do we analyze circuit? We will apply KVL to the base emitter loop and see that we will derive the equation for the emitter current here. Okay, so how do we apply KVL to the base emitter loop? There is a loop which is shown here, indicated as L here, between the base and the collector, base and the emitter here. So if we start from the ground here, we get this drop across this RB, which is IB times RB, which you can see this is the first term. Next, when we move across from RB to the base and emitter, we have a base emitter voltage VBE, which you can see here, and then followed by we have I drop across RE, which is taken as IE times RE. This is a drop across this resistor RE. We are moving from this ground to this ground of this power supply. So therefore we have minus VE. So you can see here this is minus come first, therefore it is minus VE. So minus VE is equal to 0. And from our earlier circuit analysis, we have base current is equal to emitter current divided by 1 plus beta here. This equation can be used in the first term here, since here we have an emitter current. Here you can see here the other base current can be replaced in terms of emitter current using this equation here. So now we can substitute here in place of IB here and IE related current here, IE by 1 plus beta. This is how the equation looks like. and you can transfer the voltage terms to the right hand side. This minus VE becomes plus VE, and this VBE plus VBE becomes minus VBE. And rest all terms you can take out IE as a common factor. So from first and the third term, IE can be taken as common factor here. So this is the so once we take IE as a common factor, this is how the equation looks like here. And now we can send this to the denominator. So we have IE is equal to VEE minus VB divided by RE plus RB divided by 1 plus beta. Let us label this as equation 1. Can you observe this equation? Does this equation resembles any equation that we have derived earlier? I would like to recall the emitter current equation that we have derived for classical circuit bias arrangement. Okay, what was the equation that we have derived? I will just write it here. The emitter current equation. If you have noticed the earlier equation, we have this is the equation VBB minus VBE, that was in the numerator, and what was in the denominator? In the denominator we had RB, not RB, it is RE, same as this. There is no change in the denominator. So let me write it here. So the denominator equation is RE plus RB divided by 1 plus beta. Okay, so this was the emitter current equation that we have derived for classical circuit bias arrangement with single power supply. But now you can see with the 2 power supply we got emitter current equation as this. So the emitter current equation, the one which is labeled here, is identical to the classical discrete bias arrangement, except in place of VBB in classical bias arrangement we have here VEE. That's the only difference here. Okay, and the 2 constraints that we have discussed in earlier class, namely constraint number 1 is emitter voltage VEE must be greater than VBE. That is the first constraint. Why we have assumed this? Anybody can just answer this? Why we need to assume this emitter power supply greater than VBE? Okay, what constraint, what the problem it compensates? The emitter power supply, earlier you might have noticed that in classical bias arrangement we made VBB far greater than VBE, and we have done detailed analysis on this, and we said that in order to maintain this VB variations, okay, so the VBB must be made very large. And I also told you what are the drawbacks of by making VBB, and we arrived at the trade-off which we call as the thumb rule, right? If you remember the thumb rule, VBB is equal to VCC by 3. That was the thumb rule we have used. Okay, just recall those equations. Those who are absent for earlier class, just you can recall those equations here. So same condition constraints that we have discussed for classical circuit bias arrangement also holds good here. So constraint number 1, we must ensure that here for this from this equation 1, in order to compensate for the change in VBE, we must make emitter voltage VEE, emitter power supply, very much larger. The other thing is in order to compensate for the this beta variations, so we must make RE far greater than RB divided by 1 plus beta here. So these are the changes constraints we need to apply in order to make this emitter current independent of VBE and independent of beta here. So if these constraints are applied, okay, so then you will get IE is equal to, IE is approximately equal to, okay, so VEE divided by VE divided by approximately it is RE. Okay. Okay, so I think those are the 2 constraints we were discussing. So those 2 constraints must be applied in order to ensure that IE is independent of VB and IE is independent of beta. If transistor is to be used with the base grounded, then this becomes a common base configuration, then RB can be eliminated altogether. Yes, you can see here if the signal, what we are trying to say in this last part is, if transistor is to be used with base grounded, suppose when we want to ground this base here, then this RB becomes 0, the complete circuit becomes common base configuration. Once base gets grounded here, so the configuration is the input signal we apply between emitter and the base, so therefore this becomes a common base configuration. Okay. The RB can be eliminated in such case here. The input signal is coupled to the base, then RB is needed here. So whenever we want to couple the input signal through the capacitor, then only this RB is required here. Okay, now let us solve this example, so that in order to become familiar with this bias circuit here, a 2 power supply based classical bias arrangement here. Look at the problem here. A bias arrangement which is shown in figure, this is the circuit arrangement, though we have not written circuit once again. With reference to this bias arrangement, this problem has been asked here. For a common base configuration, it is clearly told it is a common base configuration. Design the circuit to establish a DC emitter current of 1 milliampere. That means we have to design a circuit such that 1 milliampere current is established here. Just remove this other things here which is not necessary here. Okay, all right, remaining let it be, okay, no problem. Okay, so that was the problem. And see other data what they have given here. Highest possible voltage gain while allowing a maximum signal swing at the collector is plus or minus 2 volts. So that means we must design a bias circuit such that the swing here, okay, the AC signal that is coming, an amplified version here, that should have a swing. Okay, this is called as a swing, plus or minus 2 volts. Positive can go up to 2 volts and negative can go up to minus 2 volts. Okay, so this kind of swing we have to allow in the collector circuit. Okay, so the DC supply voltage VCC is given as plus 10 volts and negative power supply is given as minus 5 volts. Okay, I hope you understood the problem. Any questions are there with reference to the problem? I repeat once again the problem. We need to design a bias arrangement which is shown as a figure in the above figure, which is used for common base configuration, and we must design the circuit to establish a DC current of 1 milliampere. 1 milliampere current must be established in the emitter terminal, and provide the highest possible voltage gain while allowing a maximum signal swing at the collector as plus or minus 2 volts. We must allow the signal swing of plus or minus 2 volts. That's how we must design the bias circuit here. By providing this, the signal swing plus or minus 2 volts, some DC voltage has to be established at the collector, and that doesn't saturate, should maintain the this transistor in the active mode here. This should not get saturate, such that even the swing should be maximum here. So many conditions are, when given like this, it's quite challenging to design the bias circuit here. Let me explain this, how this problem can be solved. For your reference, the circuit has been rewritten here. You can see here the plus 10 volt power supply is given, positive power supply, minus 5 volt is V negative power supply is given, and it is told in the problem itself it is a common base configuration. Therefore, this base goes straight away to the ground. This RB will become 0 now. Even though we have shown here RB, this RB we need not use since it is a common base configuration. RB becomes 0, so this becomes a short circuit here. Alright, so RB is equal to 0 here. Now we can see right here this VBE, base emitter voltage, can be written as VB minus VE. Since VB is at the ground or 0 volts here, we can substitute that here and find out what is the VB value. So VB value is equal to now minus VE, which is, we know that VB typical value is 0.7 volts. So therefore VBE, which is equal to VE, which is equal to minus VE, which is equal to minus 0.7 volts. So once we know the voltage here as a minus, this is VE, which is minus 0.7 volts. we have taken VB. So, in this case VB and V are going to be negative. If I have a positive value of VB, negative value of V will exist here. That is what we have shown here. You can see here VB and V both are negative. Okay, so VB is opposite of VE. Okay, now with that once we know VE here, since other end we have a power supply which is minus VE, now we can find out voltage drop across this. So, voltage at this point is VE minus VE divided by IE. So, VE is nothing but which is given as minus 0.7, we can substitute here, minus VE, VE is minus 5 volts, you can substitute even that here, and IE is given here as 1 milliampere. So, IE is 1 milliampere, you can substitute all these things and find out the value of RE. RE value is found to be around 4.3 kilo ohm. So, this is the value of RE. RE is 4.3 K. Or if you understood this, any questions are there? Just to rewrite once again this one. So, this is 4.3 K. Sorry for this is writing is not good. All right. Now next part is going to be quite challenging. For high voltage gain, large voltage drop, so the problem says that we need to maintain high voltage gain, and also we need to allow the signal swing of plus or minus 2 volts as shown here. Okay, so that the transistor do not move into the saturation, it remains in active mode of operation. Do you remember the condition earlier we said how to maintain transistor in active mode? Okay, anybody can recall? What are the conditions required for the transistor to be in active mode? The VCE should be greater than VCE, collector emitter voltage should be greater than VBE. If this condition is met, the transistor remains in the active region here. So, let us assume that here the VCE is going to be around 2.4 volts. This is the assumption what we did here. Okay, so I assume that since it is told here we need to maintain swing about plus 12 volts and minus 12 volts. In other way we can say that peak to peak voltage is 4 volts. So, such kind of signal, the signal here AC signal should have positive swing up to plus 2 volts and negative swing up to minus 2 volts. Okay, so if that is the case, let us see that what will be the voltage at the collector point here. Okay, so VC we have taken as 2.4 volts, so that the transistor this VC what I have chosen here certainly it is greater than VBE, because the active mode of the transistor remains in active region, so that this works like an amplifier. Now we can find out what is VC, and this again same equation can be used. VC can be written as VC minus VE. We want VC, so VC is nothing but VC plus VE. VC is given as assumed as 2.4 and VE is nothing but minus 0.7, and if you substitute this we get to know VC as 1.7 volt. And look at here, this is at this point we have a DC voltage of 1.7 volt. That means I have a DC voltage here as 1.7 volt. Across 1.7 volt DC, the AC signal is oscillating here. Okay, so this is an AC signal. The positive goes to plus 2 and negative goes to minus 2 here. Okay, so this 1.7 that we have shown here, this is the collector voltage VC. Remember that all these voltages are measured with reference to ground only. Okay, so even the V what I said here is measured with reference to ground. Here across this, when we calculated the voltage drop, then we should take difference of this, because at this other end of the emitter resistor is connected to the minus 5 volts. Okay, so all these terminal voltages are measured with reference to ground. So we got to know that VC is 1.7 volt, that is the voltage at the collector, DC voltage at the collector. So now we can easily calculate what is the voltage at what is the resistor value RC. So this to calculate RC we can subtract 1.7 from the 10 volts here. So that's what we have here, VCC minus VC divided by IE. So 10 minus 1.7 divided by 1 milliampere. So that gives me RC as 8.3K. So RC is 8.3K. So I hope you understood this design problem. Usually, this kind of problems are quite challenging. Reason is, we have to satisfy constraints like maintaining signal swing plus or minus 2 volts, and we should properly assume this collector emitter voltage, and so that the DC voltage here is sufficient to oscillate to maintain this swing here. Okay. So again, see 1.7, again if you add the 0.7, you get back the same this 2.4 volts here. 1.7 plus 0.7 in the base emitter voltage, which is nothing but the collector emitter voltage. Okay. So this kind of problems, multiple problems when you solve, you will become familiar about the topic also. That's why every topic I end with the numericals like this. Okay, let me move on to the direct topic of today's class, which is biasing using collector to base feedback resistor. If you have understood this a 2 power supply based biasing arrangement, then this understanding of this collector to base feedback resistor becomes very easier. The figure 1 that I am going to show is the simple but effective alternate bias arrangement, which is suitable for common emitter applications here. Okay, so let us show the circuit to all of you. This is the circuit. Okay, so you can see that there is a resistor connected between the collector point here and the base. Okay, so this is RB resistor. This is called as a feedback resistor here. The current goes like this and back to the base. Okay, so this kind of a circuit is called, it is a common emitter configuration, you can see here. Okay, this kind of circuits are used for common emitter configurations here, and it is biased by a feedback resistor here. Okay, that's what the point number 1 tells you here, and this is widely used for common emitter amplifier applications here. The circuit employs a resistor RB connected between the collector and the base. Okay, this is the factor resistor which makes circuit the distinct compared to other circuits here. Okay, so the circuit employs a resistor called as RB that's connected between the collector point and the base point. Just have a look at the circuit. This is what I was talking here. So this is the collector here, and this is the base. Okay, next here, the resistor RB provides a negative feedback. We will explain in a while how this resistor RB provides a negative feedback, which helps to stabilize the bias point of the BJT. That means this has got bias point here. The bias point is nothing but VCE comma IC. This is the operating point or bias point. In order to maintain this VCE and IC constant, so this operating point, or we call this as a Q point, has to be in the active mode, and mid of the the load line, which goes across the active mode, and this VCE and IC should not vary with reference to the VBE variations, or with reference to beta variations or temperature variations. So the operating point has to be maintained constant. Now this RB that provides a negative feedback from this. Okay, what do you mean by negative feedback? The signal which is coming back here and the signal what you apply here, AC signal, which needs amplification at the base, both are going to be out of phase. Suppose if I capacitively coupled here an AC signal, okay, to the base. Okay, so this is an AC signal that is coupled here, and signal which is coming back, the signal which is coming back here, the signal which is coming back and signal which is applied here, both are going to be opposite in nature. Okay, so that's why we say here this provides a negative feedback. Alright, we'll see in more detail on how negative feedback is advantage for us. Now once we understand the fundamental circuit, here we don't have any voltage divider network in the very first circuit that we have discussed, and we don't have even the RB that's connected to the ground like previous with 2 power supply. This circuit uses only 1 power supply, which is namely the VCC. Okay, so now let us move to the analysis of this circuit. So you can see here the detailed circuit is written here with currents and voltages. Okay, so this is a BJT which is connected in common emitter mode, and there is a voltage here VBE between the base and emitter. This is VBE. Okay, and you can see this RB. Through RB the current flowing we have labeled as IB, base current, and current that is moving into the collector terminal of a transistor, which is denoted as IC, and current that is flowing out of the emitter, which is also denoted as IE, emitter current here. And now look at here, what is the current flowing through the resistor RC. So this is RC. Okay, the current flowing through the resistor RC is IC plus IB. So this IC plus IB. Okay, so that's equal to IE. Okay, so the IE emitter current, which is equal to IC plus IB, sum of this current and this current, that should be equal to this emitter current here. Okay, any questions about this? And here this equation can be obtained as VC equation here. Okay, is equal to VBE. I'll write here for your understanding here. This is VBE plus IBRB. Suppose if I consider drop from this point to ground as VC. This is a VC from this point to ground. Let me write it here, ground here, VC. Okay, plus here and minus here. Now you can apply KVL through this. Okay, in this manner, and just show the KVL like this. So minus VC, I write it here, minus VC, I am moving like this, and we have a drop here as IB RB plus IB times RB, plus we are moving from base to emitter. There is a voltage here VBE plus VBE equals to 0. On simplification we get VC as VBE plus IB times RB. So same equation is written here, you can see here. Okay, I hope you are clear with this VC. VC is very important terminal voltage, because that tells us, okay, this provides a DC, and across this AC will be oscillating with maintaining proper swing, positive and negative swing. Alright, the next we will analyze this circuit in more detail. Now we will apply KVL from the collector to the base, collector base loop. That's what it is showed here. Okay, so what we get here, minus VCC, you can see here minus VCC. I am moving from here, this ground here, to this. I already told you that you should visualize this supply like this. Okay, so minus VC like this. So this is the equivalent of this arrow mark here. So minus VCC, and while moving across this resistor RC, okay, RC times this IE. Okay, so RC times IE, and moving back to the base side, RB times IB. So RB times IB and plus VB. So plus VB equal to 0. And again we can use substitute the well known equation for IB as IE divided by 1 plus beta. Substituting here in place of IB as IE by 1 plus beta, the entire equation can be written in terms of emitter current here. So now VCC, this can be transferred to the retained here, and rest all can be transferred to the other side. So that VCC is equal to IE RC plus IE divided by 1 plus beta times RB plus VB. And here we can derive for the emitter current, taking IE as a common factor from the first and second term, and we can write the equation for IE. The emitter bias current is given by this. IE is equal to VCC minus VB divided by RC plus RB, divided by 1 plus beta. Now again we got the same emitter current equation for this bias circuit, and you have to see that how we can maintain this emitter current constant for the variations in the transistor like VBE, okay, and beta and temperature. Okay, with reference to all these parameters, we should see that whether IE is stable or not. Okay, so here like this is also equation 1 is almost similar to the again emitter current equation of classical circuit bias arrangement, but there we had VBB, and that VBB got replaced by VCC here. That's the only change. And even in the denominator also you can see that here we had RE that got replaced with RC. Okay, same changes I have denoted here. Okay, in compared to when we compare this this equation with classical bias arrangement emitter current equation, these are the changes, okay, one can notice here. Okay, now here again, to make IE emitter current stable with reference to these variations, what one should do. So how to make IE independent of these things? In the numerator, if you look at here, I must make collector power supply larger than the VBE. That's quite easy anyway, because we apply usually 12 to 15 volts as DC power supply VCC, and obviously that will be greater than the base emitter voltage, which is 0.7 volt. So this automatically compensates by having larger higher DC power collector supply voltage. But other part is to obtain IE, or to make IE which is insensitive to the variation of beta. In the denominator part you can see that I must make RC greater than far greater than RB by 1 plus beta here. Okay, if these two conditions are satisfied, okay, so one is VCC default it gets satisfied, and second thing is RC must be made larger than this RB by 1 plus beta here. And the challenge is second constraint, because maintaining this RC larger than this RB by 1 plus beta is quite difficult, because here we need to have a trade off. But look at here, what is the problem? I will just illustrate here. Here we are trying to say that RB must be small or RC must be larger in order to make this emitter current independent of this beta. The denominator has got beta term here. But when we say that make RB smaller or make RC as larger, okay, now here the swing is very important here. In order to maintain the larger swing at the collector especially, the VCB is given by IB times RB. IB just can be written as or IB can be written as IE into IE divided by 1 plus beta times RB. Look at this now here. Now since we said earlier that this VCB must be larger in order to maintain a larger signal swing, but now we see here we are saying here to maintain RB as smaller here in order to balance for the variations in the beta. So now that cannot happen, because on other side if we maintain this RB a small value, okay, so that means this VCB is nothing but the collector base voltage, okay, that has to be decreased. Now when this decreases, output voltage also decreases, signal swing also decreases here. So now here we should have a good trade off between the RB and the output signal swing here. So then only we can design a good bias circuit here. Okay, so that's all about this bias circuit, and let us work out one problem to understand this type of bias circuit well. So what is the problem now? Design the circuit which is shown in figure 1. Now when I say figure 1, that is this circuit, or even I can take up this circuit here. Okay, here with reference to this context we are saying this as figure 1 here. Okay, now we need to design this bias circuit, and let us see what data they are given. So usually the emitter current will be given, what emitter current we have to maintain here constant. Okay, so here emitter current is typically we have to maintain IE as 1 milliampere. Okay, so in order to maintain this IE as 1 milliampere, so we must design the this bias circuit. We need to calculate the value of RC, RB with all voltages and currents given. Okay, that's the problem. What data we have given, let us have a look at here. Emitter current is given as 1 milliampere, and also we must ensure that there is a signal swing of plus or minus 2 volts at the collector. and VC is saying to use 2.3 volts, and VCC is given as 10 volts, and beta is given as 100. This is a simple problem, not so difficult. Let us try to work out this. Let us write down the all given data here. You can see here, these are all the given data we have rewritten here. And now we are using VC to calculate what is the DC voltage at the collector. You can see here circuit here, this voltage here. Just I am using this equation to calculate what is the DC voltage at the collector, because from that I can calculate the signal swing. So let us use that equation. VC is equal to VB plus IB RB, and IB can be substituted as IE divided by 1 plus beta, and now we can see that V is equal to 0 in this case, because emitter is straight away grounded. Look at the circuit, V is 0 because there is no another power supply here, so straight away the emitter is grounded. So therefore the voltage here, which I call as VE, equal to 0 volts. So V is equal to 0 volts. Let us write it here, V is equal to 0 volts. Now what will happen to the VC? VC is nothing but this can be written as VCE is equal to VC minus VE. So this goes to 0. So VC will be equal to VC. VCE will be equal to VC, which is equal to 2.3 volt. Now we can substitute here VC as 2.3 volt and calculate the value of RB here. So substitute VC as 2.3, VB as 0.7, IE is given as 1 milliampere, beta is given as 100. With that the value of RB is going to be 161.6 kilo ohm here. So do not approximate this resistor value in examination. Write down the actual value, whatever we obtain from the calculations. So this is the value of RB here. So next is RC. RC can be calculated easily by applying KVL to the collector loop. Okay, so this is, look at the circuit here, how to calculate RC. RC is nothing but voltage at this point minus voltage at this point. So here VCC minus VC divided by IE or IC, that's going to be the RC. So that's what we have used here. So VCC minus VC divided by IE or IC. So substitute that, you will get back the value of RC as 7.7 kilo ohm. So these values are not standard resistor values. Usually 5% or 10% tolerance is given for the resistor value. So if this is going to be 161, if I assume that as 100K, and if I assume RC as 7.5K, so then the emitter current, you can see that how much it has been increased here. So it has increased to 1.02 now milliampere here, and the collector voltage also you can see that it is a plus or minus 2.3 volts here. So these are the things which we need to know here. Any questions about this kind of bias arrangement? I hope we have discussed in today's class a 2 power supply based bias arrangement, and even a collector to base feedback resistor kind of the bias arrangement. That's what it is, a 2 power supply based. And next bias circuit what we have discussed is a 2 power supply based a collector to base feedback. Okay, collector to base feedback resistor based biasing arrangement here. I think with that I think we have come to an end, and if you have any questions you can ask me before we wrap up today's class.